So acid-base reactions and gas evolution reactions, another two classes of reactions, and these can occur when you have the swapping of the ions, just like with the precipitation reactions. So acid-base reactions are also called neutralization reactions because you have an acid reacting with a base and they neutralize each other. They produce water or sometimes a weak electrolyte and also a salt. We use the word salt to refer to any soluble ionic compound, not just sodium chloride. Gas evolution reactions, as their name suggests, they produce gases. It's often seen as bubbling or fizzing. So let's look at the acid-base reactions first. There are different definitions of acids. We're using the Arrhenius definition, and this is the one we used when we talked about naming and writing formulas. An acid is a substance that produces hydrogen ions in aqueous solution. So we learned to recognize this HCl aqueous as an acid. When HCl, a molecular compound, is dissolved in water, it ionizes and forms hydrogen ions and chloride ions. So this hydrogen ion, let's think about what that actually is. A hydrogen atom contains one proton and one electron. If you have an H+ ion, how many electrons does it have? 0. What's left? Just the proton. So this is a nucleus? It's not even, it's the nucleus of a hydrogen ion atom, but it's only a proton. There's nothing else. So this is like crazy small thing, right? I think of this as being a little bit like, a newborn baby, a tiny human, right? I've told you that hydrogen's the baby brother of the element family. So this is like a newborn baby. Newborn babies don't go out by themselves, right? You don't go walking down the street and high-five the newborn baby who's strolling along, right? It just doesn't happen. They're always with someone. They're with an adult, either their parents or a babysitter, right? So this little tiny hydrogen ion, which is a bare proton, does not swim around in the solution by itself. It's going to ride on a water molecule. Okay, the water molecule acts like the babysitter and holds the proton, this hydrogen ion. So when you add an H+ to H2O, like this, H+ plus H2O, you get H3O+ aqueous. This is called the hydronium ion. It's got its own name. Hydronium ion. So what makes this a bit confusing is that chemists use H+ and H3O+ interchangeably. It's easier to write the equations and everything thinking of it as H+. But you have to understand that the H+ is not there by itself. It's actually being held by a water molecule. Polyprotic acids have more than one ionizable proton. So polyprotic, multi-proton. So there's more than one proton hydrogen ion that can come off of these acids. And they will release them one at a time. So H2SO4, the ionizable hydrogens are always written first. That's why you'll sometimes see hydrogens in two places in the formula of an acid. The ionizable ones are written first. So this has two hydrogen ions that can come off of this molecule. It's a diprotic acid. Those hydrogen ions come off one at a time. First, one comes off. So let's look at what that would do. Let's do green today. So H2SO4. If we lose a hydrogen ion, what's left? HSO4, and the charge will be -1. Okay, this ion has a name. It's hydrogen sulfate ion. It also has an ionizable hydrogen, and so it can lose its hydrogen ion, and then you have sulfate ion. So there's two hydrogen ions, two protons that can come off, and they come off one and then the other. Sulfuric acid is one of the strong acids. It's strong in the first ionizable proton. It is weak in the second. That's a little detail that will come up much later, probably not really until Chem 1B, but I avoid lying to you whenever possible. Any questions? The Arrhenius definition of a base is a substance that produces hydroxide ions in aqueous solution. So the most common of these are metal hydroxides, like sodium hydroxide. This dissociates in water, forming sodium ions and hydroxide ions. There are bases that do not have hydroxide in them. Ammonia is one of those. Ammonia produces hydroxide ion by taking a hydrogen off of water molecules. And this should be an H+. So when you put ammonia in water, this is a weak base, the ammonia will take a hydrogen ion from a water molecule, and then what's left is the hydroxide ion. So acid-base reactions are all about passing a hydrogen ion back and forth. Whoever has that hydrogen ion is the acid, and whoever passed it off was the base. Oh, forgot this part. Some bases produce 2 moles of hydroxide per mole of base. Things like calcium hydroxide, CaOH2, would produce 2 moles of hydroxide. We don't have a special name for them. And they do just completely ionize, so they don't do it one at a time like the acids do. So in a neutralization reaction, the hydrogen ion that's released from the acid combines with the hydroxide ion released from the base, and those make water. So that's this equation down here. H plus OH minus makes water. We can predict the products and write balanced chemical equations using the same process that we did for precipitation reactions, pulling the ions apart, seeing what they are, and swapping partners, stick them back together, see who has chemistry. So here we have hydrogen ion and chloride ion, sodium ion and hydroxide ion. So we're going to swap the partners. We're going to put sodium with chloride. That's going to give us sodium chloride, and we know from the solubility rules that's soluble. This one is not maybe as obvious. When we're swapping the partners here, we've got H plus and OH minus. This one was Na plus and Cl minus. So if you just put those two together, just thinking about ions and their charges, you've got +1 and -1. You shove them together, and you get HO. Like, that looks funny. Okay, this is 2 H's and an O, right? That's water. So H plus and OH minus together make water. We just write it as H2O. If we write the complete ionic equation and cross out the spectators, we find that the reaction, the net ionic equation, is this: hydrogen ion plus hydroxide ion making water. And that is true for many, if not most, acid-base neutralization reactions. As long as the salt that forms is soluble in water, this will be the net ionic equation. Any questions? So let's look at picture here. Here we've got hydrochloric acid, and this is a representation of what the hydrochloric acid is doing in water. It's a strong acid. It ionizes completely. It forms chloride ions and hydrogen ions, but the hydrogen ions are going to ride around on the water molecules because they're too small to be out by themselves. So we have these hydronium ions. Here we've got sodium hydroxide. The sodium ions and the hydroxide ions dissociate completely, so we have sodium ions and hydroxide ions. When we mix these two solutions together, the hydroxide ion will say to this hydronium ion, hey, I see you have an extra proton you're carrying around. I'm actually short a proton. I'll take that off your hands. So this hydronium with the extra H plus gives that H plus to a hydroxide ion. And then they both are water molecules. Okay, so we've got all the hydroniums and the hydroxides pairing up and exchanging, passing off. So it's like, okay, everybody's just got their 2 hydrogens now. And then what we have left in the solution is just sodium and chloride, salt water. So you can mix sodium hydroxide, which is used as oven cleaner and drain cleaner and is really, really bad if you drink it. I mean, just horrendously bad. We've got hydrochloric acid, which is in your stomach, but, a more concentrated form of that is also very damaging, right? You mix them together, the acid and the base neutralize each other, and now you've got salty water, which isn't going to taste very good. And if you drink too much of it, you'll get dehydrated, but, it's not going to kill you. This is the table that we were kind of missing earlier. Common acids and bases. So this is where the book lists the 6 strong acids. So these are the strong acids. Strong meaning they ionize completely. Here are 3 of the common weak acids. Everything that's not a strong acid is a weak acid. So there's lots and lots and lots of them. You need to know the 6 strong acids, and then every other acid is weak. So here's formic acid, acetic acid, hydrofluoric acid. Notice in these formulas for formic acid and acetic acid, there are hydrogens in more than one place. They're not all at the beginning. And that's because only the ionizable hydrogen is listed first. So formic acid and acetic acid both have 1 hydrogen ion. They're monoprotic acids. Okay? HF is also a monoprotic acid. Here for bases, any soluble metal hydroxide is going to be considered a strong base. Calcium and barium hydroxide are not as soluble. They're kind of in the middle between soluble and insoluble, but they are bases, strong bases. So if you see metal hydroxide, you can be pretty safe saying that's a base. Ammonia is the only other one that you need to remember. Ammonia is a weak base. And I showed you this equation earlier. Ammonia reacts with water, taking a hydrogen ion from the water, in that way forming hydroxide ion. An Arrhenius base is a substance that when dissolved in water forms hydroxide ions. So ammonia fits that definition. Any questions? So let's write an equation. We're asked to write a molecular and a net ionic equation for the reaction between aqueous HBr and aqueous LiOH. So we'll start off with our reactants, HBr. Does somebody in the back corner there want to close that door? Christian can be a little loud sometimes. Thank you. So here, there we have our equation, our reactant formulas. So we're going to do the same thing we did with precipitation reactions. We're going to write the ions that are present in those 2 substances, and we're going to switch the partners. So HBr has H plus and Br minus. Lithium hydroxide has lithium ions and hydroxide ions. Remember that you can only split it into 2 ions. You can't make 3. So then we're going to swap partners and write them over here by writing them underneath with their charges. It makes writing the formulas much easier. You just rearranged. Again, it's always cation and anion, just because it's convention. So H plus and OH minus, you shove them together, you get HOH, which looks weird, and you say, oh yeah, that's right, that's H2O. Unless otherwise specified, we assume that this is happening at room temperature, and so water will be a liquid. And then we need to put Li plus and Br minus together. So that would be LiBr. And we can predict its solubility from the solubility rules. The first line in the table says that lithium, sodium, potassium, and ammonium compounds are always soluble. So this will be aqueous. So this is our molecular equation. I'm going to call that Me. Okay? So that's part of what we're asked to do. Is this balanced? Yeah, it is. Here's two hydrogens, two hydrogens. A Br, a lithium, and a lithium. And there's one oxygen here and one oxygen there, so it's balanced. To do the net ionic equation, you need to look at the complete ionic equation. And so since we don't actually have to write it all out beautifully, we can actually just use these guys down here to help us figure out what is going to be a spectator and what isn't. So for ionic equations, if it's aqueous and not a weak acid, then you separate it into its ions. So HBr is on that list of strong acids, so it ionizes completely, and so it's going to get split into ions. Lithium hydroxide is a soluble ionic compound, split into ions. What about H2O? We can't split that one. So in the complete ionic equation, that would be written as H2O. And then this is soluble ionic compound, again with the ions. So now we can look and see what ions occur on both sides. Here I've got bromide. So nothing happened to the bromide, and nothing happened to the lithium. And so what I have left is hydrogen ion plus hydroxide ion making water. And that's the net ionic equation. I have no idea what's up with my voice today. Any questions? Let's do another one. Net ionic equation for reaction between that's formic acid, HCHO2, a weak acid. They were like really thoughtful here and pointed that out to us. And aqueous sodium hydroxide. Even though they don't ask us for a molecular equation, it doesn't hurt to start writing one. So there's our acid, so that's aqueous. And we've got sodium hydroxide. We need to predict the products so that we can eventually get to the net ionic equation. So this does form ions. What you're going to do is you're going to take the hydrogen off the front. So it's an acid. It's going to release a hydrogen ion. And then everything else is the anion. And you're like, I don't know what CHO2 is, CHO2. You don't need to know what it is. It's formate, but you don't need to know that to do this sort of a problem. If there's one hydrogen and one of those weirdos, then this is +1 and that's -1. And that's all we need to know about that. Sodium hydroxide we should be good with. Sodium ion and hydroxide ion. And then again, we're swapping partners. We're going to put the H plus and the OH minus together. We're going to put the sodium with the weirdo. So H plus and OH minus makes water. And this is sodium and formate, and based on their charges, we can say this is NaCHO2. And because sodium compounds are always soluble, no exceptions, we can say that's aqueous. So that would be the molecular equation. If you check through it, it is balanced. But we're asked for the net ionic equation. So the net ionic equation, we're not going to break water into ions because it's a liquid. It's not a soluble ionic compound. This is a soluble ionic compound that breaks into ions. Sodium hydroxide breaks into ions. This is a weak base. Got to watch out for those. A weak base only ionizes a little bit. And in the ionic equations, we write what is most present. So most of it is going to be this molecule. So we're not going to do ions for that either. So we're going to write this, and we're going to separate that. We're going to write H2O, and we're going to separate these. So what are the spectators? Yeah, question?
Why did you say you weren't going to break that one?
We're not going to break this one because it's a weak acid. And weak acids only ionize a little bit. So this time we only have one spectator. What is it? Sodium. Sodium appears unchanged on both sides. So get rid of the spectators, and then we're going to write down what's left. So we have the weak acid. And then we have hydroxide ion. That's to make water. And CHO2. Any questions? Remember, going from molecular equation to ionic equations, you separate aqueous substances except for weak acids. You do not separate anything with an L, a G, or an S. You just copy down the entire formula. So the weak acids, that's the one that's going to trip you up. So sometimes we have to say, well, you know, I can't master all of it. I have to settle for good enough. I'm just trying to barely get through this class. If you're in that camp, if you forget about the weak acids not separating, you'll probably still pass the class. That's not going to be a deal breaker. If you can't do stoichiometry, yeah, that's not good. But if you forget about the weak acids not separating, that's not the end of the world. So acid-base titrations. This titration is an experimental technique. We're actually going to do a titration. I think you guys will start that on Monday. We take a substance in a solution where we know the concentration, and we mix it with a substance in a solution where we do not know the concentration. And by measuring the volumes of each solution and knowing the one concentration, we can find the concentration of the unknown solution. It's a very common, very useful technique. So we add one solution to the other until the reactants are in their stoichiometric ratio. That's known as the equivalence point. You've added just enough so that all of it reacts. And then we can calculate the unknown concentration. Well, the trick is, how do you know when you've added just enough, right? You have an acid and base solution, you mix them together, they're both colorless. The solution that's being formed is colorless. How do you know when to stop? Well, there's different ways to detect that equivalence point. The easiest is to use an indicator. So an indicator is a compound that will change color based on whether the solution is acidic or basic. At the equivalence point for an acid-base titration, the moles of H+ are equal to the moles of hydroxide. So here we have an illustration and actual pictures of a titration. So we use a burette and an Erlenmeyer flask. In the Erlenmeyer flask, we have our solution of unknown concentration. It's got hydrogen ions in it. We're not showing the spectators. Here's our burette. It's got sodium hydroxide in it. We're not showing the sodium ions because they're spectators. We know the concentration of the sodium hydroxide. We've got it in a burette so that we can dispense in a very controlled way as much as we need, and then we can also measure the volume that's dispensed. So we add some sodium hydroxide. The hydroxide ions react with the hydrogen ions and neutralize them. We have an indicator in here called phenolphthalein that will turn pink when there's a little bit of extra hydroxide. So we add some more, and now we've neutralized all of the hydrogen ions, and that's the equivalence point. We stop adding when we get that pink color, and then we can measure the volume of this. We know the concentration. We know the volume of this, and so we can figure out the concentration of the original solution. This is what it actually looks like when you're doing it. You've got a clear solution. It looks like you're adding water to water. After a while, you start to see a little bit of pink as you're dropping the sodium hydroxide in here. But if you swirl it, it will go away. You get localized pink here because when the sodium hydroxide first drops in, it's more concentrated right there. And if you give it a swirl, it'll mix around and be neutralized, and the pink color goes away. You keep going until you get a pink that remains for at least 30 seconds. This is way too pink. This has overshot the end point. But a real pale pink like we're supposed to get is really hard to show in a photograph. So let's do a calculation. A titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? The way we solve titration problems is by using stoichiometry. It basically comes down to solution stoichiometry, which we have already covered. You do not use the dilution equation. A dilution is when you have one substance, you're adding more solvent and just decreasing the concentration, diluting it. Here we have an actual chemical reaction occurring, so you cannot use the dilution equation. We need to start out with a balanced chemical equation so that we can know the mole ratio between sulfuric acid and potassium hydroxide. So H2SO4 plus KOH. You might be able to predict these products without writing out the individual ions, but maybe not, so let's write them out. So those are the ions present, and we're going to swap partners. And we're going to have K plus and SO4 2 plus. So the H plus and the OH give us the water, which is very typical of acid-base reactions. Over here, by looking at the charges, we can see that this product is K2SO4. And solubility rules help us to predict that that's soluble. Is this balanced? No. Over here, I've got 2 potassium ions, and here I've only got 1. So I need 2 of those. And then if I count up the hydrogens, I've got 2 hydrogens here and 2 there. So I need 4 and 2 water molecules. Let me get rid of this because this is in the way now. Whoops. I got this guy over here. Okay, let's take the numbers and put them under the equation. So 20 milliliters of the H2SO4. 22.87 milliliters of KOH. And they give us the concentration, moles per liter. So that's all the numbers. Remember, write this capital M as moles over liters so that you recognize that that has per in it. That's a conversion factor. And they're asking us to find what? Concentration of the H2SO4. What unit do they probably want? Molarity, right? So question mark here, moles per liter. So we're going to approach this as stoichiometry. The regular path is grams to moles to grams. We don't have any grams. So we're switching up the beginning. What we've got is milliliters. And then what do we want at the end? Well, it's asking us for moles per liter. We know the volume here, so what do we need to calculate the molarity? We need moles, right? So we actually don't want to do that last step at all. We want to stop here at moles of sulfuric acid. Then if we divide by the volume in liters, we'll get the molarity. Okay? So we're going to start with the KOH. We start with what we know, and we're going to what we don't know. So 22.87 milliliters. Oops, forgot to say what. Milliliters of what? KOH. We're going to moles of KOH. We're going to moles of H2SO4, and we're going to stop there. Here we've got that milliliter-liter issue again. There's different ways that you can handle this. One of them is millimoles. So if I put milli in the top and milli in the bottom, that can work out. Then you'd have to make this into millimoles as well. But then when you divide by milliliters, the millis will cancel out and everything will be nice. So if that made sense to you, go ahead and do that. Otherwise, I think this might be the better approach. This is similar to what we did when we had kilograms being annoying in there. I'm just going to set the milli aside. Milli means times 10 to the minus 3. I'm going to cancel out the liters and leave the milli. The other thing you can do is you can take this volume and convert it to liters and then do the stoichiometry equation. So at least 3 ways of doing it. Do the one that makes the most sense to you. So here I've got moles per liter. That's the concentration of potassium hydroxide that I was given. So 0.158 moles in 1 liter. Mole ratio comes from the coefficients here. 1 mole of H2SO4 needs 2 moles of KOH. So if I do this, I get 22.87 times 0.158 divided by 2. So I'm realizing I did this different in the other section. Not necessarily a bad thing. I'm ending up with millimoles. if I take that and divide by my volume in milliliters, the millis cancel out, and I can get the molarity. I'm guessing a lot of you aren't going to like that. I didn't intend to go there, so let's fix this up a little. Let's convert our volume to liters first. That's what most students seem to prefer. Converting from milliliters to liters involves moving the decimal point 3 places. Students don't seem to have any problem with that. What messes you up is what direction do I move the decimal point? So use the bigger, smaller rule. So I want to make this to liters. Which unit is larger, milliliter or liter? Liters are bigger. We now have experience with 10 mil graduated cylinders. You can eyeball how much a milliliter is. It's not very much. We also know how much a liter is. It's half of a 2-liter bottle of soda. It's bigger, right? The bigger unit needs the smaller number. The smaller unit needs the bigger number. So I want to move the decimal point 3 places to make the number smaller for the bigger unit. So 0.02287 liters. Or write it out with the milli and the liter and the 10 to the third and everything. So here, I write 0.02287 liters. The liters cancel down here, and then what I end up with is times 10 to the minus third moles. Or 0.0018067 moles. Molarity is moles over liters. That's what I'm trying to find. So I'm going to put the moles, 1.8067 times 10 to the minus third moles. And I need to divide by the volume in liters. So I also have to convert 20 milliliters into liters. Again, I'm converting from a small unit to a large unit. I'm going to move the decimal point to make the number smaller. Big unit, small number. Small unit, big number. So this is going to be 0.0200 liters. And there we go. That's the concentration of the unknown sulfuric acid. When you're first learning how to do a problem like this, it seems confusing and tedious and difficult. Once you can kind of step back and see what's going on here, it's actually much easier than doing mass stoichiometry. We don't have to go looking or calculating any molar masses. We're using molarity, and that's given here, and then we're finding the other one. And so it's actually much more straightforward. This ratio here is exactly why you cannot use M1V1 equals M2V2, because that does not take into account the stoichiometry. What's especially dangerous about it is that if the stoichiometry is 1-to-1, it works and you get the correct answer. But if it's any other stoichiometry, it doesn't work and you get the wrong answer. So my advice is never, ever use the dilution equation for titration. Any questions? Okay, what about the gas evolution reactions? Sometimes when you look at the ion exchanges, like between potassium sulfide and sulfuric acid, you swap the partners, you get potassium sulfate and H2S. H2S looks like an acid, but it actually is not very soluble at all in water, and so it will come out as a gas. And how are you supposed to know that? You just need to remember it. H2S is a gas, and it smells really, really bad. Other reactions form a gas by making a substance that then decomposes into a gas. So sodium hydrogen carbonate, baking soda, plus hydrochloric acid makes sodium chloride and carbonic acid. Carbonic acid isn't stable. How do you remember that? Well, you just have to remember that. Carbonic acid isn't stable. It'll decompose into water and carbon dioxide. And the carbon dioxide will bubble up. That's what's happening in a soda. So here we have an illustration of this process. So we get carbon dioxide bubbles that form, and because they're a gas, they will rise to the top and pop and escape. So you do need to know the 4 groups in this table. The first one is that H2S. If you swap partners and one of them is H2S, the correct state symbol is G. Because these guys, if you get carbonic acid, sulfurous acid, or ammonium hydroxide, you need to remember that those 3 substances are unstable, and they will decompose to form water and a gas. And knowing what gas they make is actually not that hard. So I'm going to show you how that works. Just to mix up, I'm going to start with the one at the bottom. Ammonium hydroxide. So that decomposes. All of these lose 1 water molecule. The gas is what's left of that formula. So I need to take off 2 H's and an O. Well, there's the O. Get rid of that H here, and then that makes this 3. So NH3. That's ammonia. That's the gas. Sulfurous acid. A water molecule leaves, and the gas is everything that's left. So here's 2 H's, and we need to get rid of 1 of the O's. So what's left is SO2, and that's the gas. Also smelly. Most things that have sulfur in them do not smell pleasant. Carbonic acid also loses a water molecule. So get rid of 2 H's and 1 of the O's, and we have our little friend carbon dioxide, which is a gas. Okay, so there's some more material for your flashcards. If you've got H2S as a product, it's a gas. If you have one of these, it's going to decompose and form water and a gas. Any questions? Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfate. What's nice about all of these reactions that we're looking at now is it's the same idea. Write the ions with their charges to help you get the formulas. Swap the partners, stick them together. That's how you get your products, balance the equation. Same basic idea for all of these. Hydrobromic acid. The hydro tells me that this is a binary acid. It doesn't have oxygen in it. So it's just hydrogen and bromine. And aqueous potassium sulfite. So potassium is K+, sulfite is the light version of sulfate. So it's SO3 2-. So I'm going to HBr, that's aqueous, and this will give me K2SO3, also aqueous. Predicting products, we're going to swap partners. So I'm going to get K plus with Br minus. I'm going to see what they do. So that's going to make KBr. And solubility rules tell me that's soluble. And then I've got to put H plus and SO3, 2 minus together. And that will give me H2SO3. That should go ding in your brain. Oh, hey, I think that's one of those. It is. It's one of those that decomposes. And what it does, it loses a water molecule. And then we look at what's left. So we get rid of both of the H's, we get rid of one of these oxygens, because those are in the water molecule. What's left is SO2. So up here, where it says H2SO3, I'm going to write H2O liquid plus SO2 gas. And that's my molecular equation. Is it balanced? No, it isn't. Here I have 2 potassiums, and here I only have 1. So I need a 2 over here. Excuse me. 2 bromines. Over here I only have 1 bromine. So we gotta fix that up. 2 bromines over here. Now this is a reaction where the sulfite does not stay together. It does come apart. So we do have to look at the sulfur and the oxygen separately and make sure that that's okay. Let's check our hydrogens first. 2 hydrogens and 2 hydrogens, so that's okay. Over here I've got 1 sulfur, and there I've got 1 sulfur. I've got 3 oxygens. I've got 2 oxygens in the SO2 and 1 in the water, so that's okay. Any questions? You guys are really quiet this morning.